Our second speaker is Iosif Lytras. He is a postdoc research fellow at Archimedes Research Center for Data and Algorithm. His research interests lie in the algorithm for machine learning problems and their convergence analysis. He will be speaking about Taming under Isoperimetry. Iosif.
Okay, thank you for inviting me to the event. It's a lot of stuff.
Oh, I could sing. But you wouldn't want me. Will you pay me for it? Okay. So we're kind where we're going to talk about sampling from through Lanzamin the diffusion. I will skip this part. I will make it really quick because all of you are really experts in these things, and then go through a part of our work, which is the taming through the language of log-Sobolev inequalities and Isoperimetry, and then some independent work in the same paper with which they try to prove some more constants in different scenarios. Okay, so for here, P beta will be our environment measure of interest, and H will be the gradient of U. Standard stuff, we know that under mild conditions, it's the unique environment measure of the Lanzamin energy. So we will use the Neurer-Mariaman scheme. One can have either a constant step size or a decreasing. We only deal with constant step sizes. And so the first, the vanilla Lanzamin algorithm is the EULA, which can be written this way. Here, psi will be Gaussian random variables, standard stuff. Okay, so let's talk about the prior work. The first results were under the standard results are under Sokovexty and global Lipsness. And the question is how to go beyond this stuff. So ideally, we want to go non-convex and local ellipses. So now we care about superlinear gradients. So we go local ellipses. We don't care about Helder, which other works. And one can see if, even for the vanilla EULA, and if you have this really simple function, even in one dimension, after some very simple calculations, one can see that these moments have this lower bound. So as n goes to infinity, we have this explosion, even in one dimension. So this, it seems that we have a problem if one applies EULA naively. So there was beautiful talks by Ian Sotirios in the first week that explained this stuff. So I'm going to pass through very quickly. That showed that there was the theorem, the negative result of Hadz and Haller, that if you have a superlinear in one of the coefficients, either the diffusion or the drift, then we have explosion of the moments, and this justifies the phenomenon that we saw in the very simple example. So the solution to this problem was taming. So what is taming? Essentially, you want to make the drift linear, but having kind of converging to the initial drift that you want to approximate. And the first work was by Hadzenhaller, and then was extended by Sotirios. Many works since then. It's been standard literature in the numerics for SD. And it's not the first time that one visits this in the sampling literature. So there is a very nice work with Brosset, Alain Durmus, Sotirios, and Eric Mullin. And there is also a work in stochastic gradients for SDLD, which was with Miklos, which is somewhere there, Sotirios, me, and Attila. And some recent work which Yin has done with her collaborators. So these works have, I will gonna go to the comparison now. There, in our paper, there is a clear analysis. So we either improve the assumptions or the constants or study different distances from these settings. So what we're interested now, we want to study the log-Sobolev inequality and how one proceeds with it. There was a talk of VC Borno yesterday, so a lot of work has been done for me, so I will speed this up. But the idea of the log-Sobolev inequality is that it can see that as an optimization in the space of measures, then if you write it in Marin structure induced by W2, then it's the analogous of the APL condition. So in optimization, when they go to gradient descent and want to go from strong convexity to some less assumption, they use this PL condition so that the gradient dominates the function. So and this is the analogous in the sampling. So that the Fisher information dominates the relative entropy. Okay, there are a lot of stuff known about these log-Sobolev inequalities. At the strong convexity, there is the Bakry-Emery theorem, and it's also stable at the perturbations, under Lipschitz mappings, convolutions. And there's also the theorem of Catio that says that if you had dissipativity, one side Lipschitz and Poincaré, then you also have log-Sobolev inequality. And of course, there are a lot of results, but I just showed some basic examples. So let us now focus on our work. So what we assume here is actually dissipativity and local Lipschitz for the gradient. So this is allowed to go superlinearly. So if one applies vanilla Euler, it will not be stable. We assume that our measure satisfies log-Sobolev inequality. And then we have some, okay, the initial condition could be a Gaussian, okay, no, very mild. And this is more technical. Probably it can be proved, of course. I don't believe that this is really necessary. I will discuss about it throughout the proof. So we propose a new scheme that has some different elements that play a role here. Instead of directly taming the drift coefficient, we first split it with the linear part that has to do with the dissipativity terms, and then tame this part. This will enable us to get the dissipativity condition now for the drift coefficient. So this enables us to get uniform moments. But it's also very important in throughout the proofs. And then here we tame, this will be bound, will not be just linear. We just tame more because this is the power of the high Poisson derivatives. So this will play a big role in our proofs. So under these conditions, what we achieve is our drift has linear growth, but this linear part here is independent of this step size. Of course, we need it to be close. It's lambda close to original drift, but it's also 1 over the square root of lambda Lipschitz. And this is this part, actually not this part, the way that this is constructed plays a role here. So we are able to derive a dissipativity condition that in previous works there was assumed just by square dispativity. We will have it now for the drift coefficient. Of course, while in dispativity, if one has worked in these things, dispativity is needed to have uniform stability. So for n iterations, we have uniform moment bounds, very mild assumptions in the step size. The lambda here is comes from the constant of the local Lipschitz, but it's here in this constant. Nothing crazy. And we're able to have uniform bounds. In the paper, they are given explicitly, polynomial dependent dimension, as expected by the Gaussian noise. So in order to work, we want to work with continuous arguments. So we will go to the continuous time interpolation. And what is special with the continuous time interpolation? That of course it agrees at grid points with our algorithm. So essentially, writing this way, we will also have moments for the continuous time interpolation because we have uniform moments for the algorithm. So if one goes back here and freezes conditions on the previous step, of course, this is a Gaussian, right? So the idea is that since this is a Gaussian, we can directly write the Fokker-Planck. And using this, one by doing some Bayes theorem application, can write this stuff and produce something for the density of the continuous time interpolation. Well, this is standard work, but that has been done with Van Pala and Visiborno. But here, the different and difficult thing is that we have this drift term. And for one to be able to really show that we have this change of integrals and derivatives and has to be rigorous, that's why we had these extra assumptions for the upper derivative. So this is not trivial work, and we have to do everything rigorously. So one here is able to construct this this expression for the derivative of the KL, and by doing a divergence theorem, one reaches this. Again, this the choice of how we construct this drift plays a role here to prove that we can do the divergence theorem, we can do anything rigorously. So after calculations, one reaches this difference inequality. And of course, that's why we assume the log Sobolev. Here, this part becomes this part. So our inequality will only have terms that involve the relative entropy. So here we have some terms that we have to bound. We split this term into two. And of course, here is where the approximation of our term scheme to the original plays the role, which is over log lambda times the uniform moments that we have. And this will be controlled by the local Lipschitz and the one step of this approximation. So again, all this term will be of lambda. So after everything, we have the forgetting of the initial density, and we have the bias here. So here this C hat is polynomial dimension, just depends the moments of our algorithm, nothing not expected. And here we see that this bound, of course, depends on the log Sobolev constant. And why we do this? Because if one works with relative entropy, then one can go to other distances. By Talagrand, we go to the W2, and by Pinsker, we're able to also control the total variation. So this also enables us to have an optimization guarantee. So if U star is the point, the value at global minimum, we can get these results by decomposing into the sampling problem and the concentration around the minimum. Here, we know as beta goes to infinity, this will become small. So we first pick beta, that this term becomes small, and then we pick lambda, and then that, of course, that goes to 0. So we also get a global optimization guarantee. So essentially, this work was kind of extending the results of Ebola-Borno in a more complex superlinear case. So the other part of this work, up to this moment, do you have any questions before we proceed? Because then we'll change the scenery. Okay. So if you see here, this bound is influenced by this term. So of course, one begs the question, how big is this term? What we can say about this term? So the other part of the paper is to survey some results that we can produce about these terms that are relative in our setting. So what we prove here is that if one has a local ellipseness and our function is strongly outside of a ball, this is not easy to interpret because this is a non-convex domain. But if one sees the definitions that we have on our paper and our analysis, and is able to define this in some way, and then we can see that the environment measure will satisfy an LSI with constant, which is independent of dimension. This is essentially important here because in some machine learning tasks and in some algorithms, such as Theopula, one adds a regularization term. One can see that if I have a G and then add some regularization, then essentially I will get this strongly complex outside of some property. And then this regularized measure now will have a log Sobolev inequality, which is independent of the dimension. So, how much time I have? Okay. Okay, so we can see quickly the proof here. What we do, we write it this way, and we try to extend the function u out of this ball, and then modify. And this way we create a bounded perturbation of this u hat. But the very important is that the bound that you create is independent dimension. So essentially we have now a u hat which is strongly convex, but has a Hessian. That's why we did the modification everywhere, and it's kind of bounded from our u. So I suspect, because I know that you people are experts in this, we can have a log Sobolev inequality for this u hat. And then because it's bounded from our initial u, we use the Hulle-Strock perturbation theorem. It's the technical part here, that because you have to deal with these strongly convex outside of convex domains. But other than that, the final part of the proof is very reasonable. So yes, that is about the log Sobolev constant in the case that we are convex at infinity. So what happens Poincare inequality? Poincare inequality, we know it holds when you are only convex. lot of results, but we try to survey a case where one can have some kind of independent on the dimension and improve bound on beta Poincare constant. So we have the following assumptions. We have that local ellipseness assumptions again, gradient, the Hessian being dominated by the gradient. These are and non-generate critical points, which means that my saddle points will have an escape. So the minimum eigenvalue will have will be less than minus lambda, and the local minimum will be greater than that. And we also have this assumption that we have a unique local minimum. We will discuss in the end about this and how it plays the role. So under these assumptions, and assuming that after some ball, our gradient goes away from 0, which is also reasonable, we're able to show that if beta is big enough, our eventual constant has nothing to do with our beta and the dimension. So how to prove this? And here we'll have the discussion why we need this unique local minimum. So we split the domain in 3 regions: near the local minimum, away from the critical point, and near the saddle points. So first, what we do here, we will show a Poincare inequality on U, and these balls of radius R are put in a way that they are controlled by beta. So because of the choice of beta that we make, here we will be strongly convex near this, in this ball around the local minimum. So this is very easy, Bakry-Emery theorem. So by standard arguments, we are able also to prove that away from the critical points and near this point, we have a Lyapunov function that has this form. For those people who have worked with Poincare inequalities, these parts are really standard. So from here, one can see that from if we have a G that is vanishing on the boundary, one can have this expression. If here was RD, then would be okay, but here we need a subset. So we have to make the boundary term 0. So the interesting part here goes here. How to handle the cases where we are near a saddle point. So what we do here is that we prove that the larger SD has a sub-exponential escape from saddle point. And what this enables to do is to be able to have a new Lyapunov function that handles this part of our domain. So essentially, we can find that if G is vanishing on the boundary, we have for this new Lyapunov functions different from the previous one, we have this bound. Okay, you say so you have 2 different Lyapunov functions. Who cares? How do you put them together? Natural question. So how to do that? So this is a very neat construction that you prove, you build here an X bound function so that X will vanish on the one boundary and 1 minus X will vanish on the other boundary. Why we do that? Because the functions that we want to produce, we want to have this property to vanish on the boundaries in both cases. So if we write F squared this way, and then I'm proud to prove a Poincare inequality, we get this term. So for the first term here, we are able to apply the first result because this vanishes on the boundary. And the other result with for the other Lyapunov function, because again, this vanishes on the other boundary. So putting everything together, one gets this variance bounded by the gradient, which we want to prove, plus something here, which is the variance for the restricted measure on U. So that's why, so everything here up to here would work with having not the assumption for a local minimum. So essentially here we have kind of control this Poincaré constant around this U. So because we have one local minimum, we were able to get a very good Poincaré constant here. But up to this point, the local minimum doesn't play any role. So if U is, which is the union of the balls around the local minima, has a good structure, for example, this could also be, we may have a very nice Poincaré constant. In our case, this constant is completely dependent dimension. So putting everything together, one gets a result where everything here is independent dimension. But what we have done is that the assumption of B, that B should be bigger than some power of D. If we are in a very general case, everything would pass up to this point, but here we will have an exponential on beta. So the final part is that we are able to, of course, upgrade this to a log-Sobolev constant using the results of KTO by assuming dissipativity and one-side ellipseness. This Poincaré constant can be upgraded to a log-Sobolev constant where has this dependence on beta. So this paper can be seen here in archive. And for some part of it, there is an extension for Poincaré equality and wicked dissipativity in a new work by me and my one collaborator. So thank you.
Hey, so am I right in saying that if you don't add the regularizer term, then the constants blow up as equals to infinity?
Which part? Which part?
Yeah, I think so. So if you don't add this regularizing term, or then the constants blow up.
And you're talking about
Yeah.
depends on the structure, but what I was saying that you may have some Poincaré constant, but we haven't assumed anything else here other than locality.
Okay. Yeah.
So what I say that if we have regularization, which happens in machine learning, and this is high enough regularization that this R is connected to this L,
Yeah.
then you have this kind of strongly convex
outside of the ball, rigorously defined in the paper, what we mean by that. And so we have a log-Sobolev that independent dimension.
I see. Yeah. Okay, that makes sense. Thank you.
One more question. Probably I have a quick question about when you design this tamed algorithm, you have the assumptions, and
yes.
it is this L. I see you have an L in the exponent here.
Now here.
This L is
Yeah.
is related to the growth of H, right?
Yeah, and it's also related to the multiplication.
Okay.
Because at some point, when you do some calculations and you want to make ellipses, when you want to make ellipses because it's easier to show that some integrals exchange with the derivative. Then in order to have to show those ellipses, ellipses for let's see for here. I think it's
And the upper bound for the tame thing is next slide. Here is really you have this separated. This x is not multiplied with 1 over square root.
yes, that is one benefit that you get. So in some calculations that I think in the future this kind of work helps in some calculation not have this much weight on the x value.
This is because you have this specific design of this. You have AI.
But yeah, so everything comes from here in the linear part.
Okay, so this L is chosen such that the second term is bounded. Thank you. If there are no other questions, let's thank the speaker again.